Now here comes our next presentation
I have.
by Meshcheryakova. I hope that I pronounced correctly. And with the
Sorry,
presentation,
can you hear me?
modeling of fatigue wear in rolling contact of elastic bodies. Welcome.
Good afternoon, all participants and listeners. Sorry for this pause. And today I will present some results of the modeling of fatigue wear in rolling contact of elastic bodies. My name is Meshcheryakova, and this work was supervised by my supervisor, Professor Irina Goryacheva. Under cyclic loads, an inhomogeneous cyclic field of internal stresses arises in elastic material. For example, in railway transport, the fatigue wear of rails in wagon is one of the most common type of damage. The development of high-speed trains and also the growth in carrying capacities increases the level of requirements for rails. In particular, traffic safety increasing the resource of rails. To choose the path how to develop the rail material and other parameters, we need to understand the mechanics of fatigue wear in wheel-rail contact. On the right side of the slide, we can see some examples of the cracks in the rail surface under the load. And on the next slide, we can see also the photograph of the typical metal delamination on the rail surface on a railway. And the nature of the formation of these defects is mostly determined by the stress state of the wheel and rail, which depends on several factors, like load, slippage, profile of the wheel and rail, speed, and etc. On the right side on the slide, we can see the scheme of the correct delamination in rolling contact. Here, the shear deformations in the rail material caused by the large longitudinal cleavage in the wheel-rail system. And the aim of this study is to analyze the stress state of elastic half space under the roller and also calculate the wear kinetics in rolling contact. I will say some words about fatigue wear modeling stages. This scheme is mostly taken from the book of Goryacheva Irina, and here, as I said earlier, the fatigue wear is mostly determined by the stress state of the bodies. So at the beginning, we need to solve contact problem for elastic bodies in rolling contact. After that, we need to calculate the stress state of elastic body. And in the third, we can start to model fatigue crack initiation and the growth after the critical damage value is reached. For this, we need to choose the damage criterion and also the model for damage accumulation. And after that, we can calculate the damage in the elastic half space, taking into account the damage present in the contacting bodies with the changed microgeometry. I mean that in fatigue wear, the fracture can occur again and again, so we need to take into account the history of this process and recalculate the contact stresses and also the stress state of the elastic half space. In this study, we consider a three-dimensional contact problem about rolling sphere on the elastic half space. we consider that the sphere and the elastic half space have the same elastic modulus, and also the speed, the running speed of the sphere is constant. To describe this problem, we can take two systems of coordinates, moving and stationary, and on the left side of the slide there is a relation between these two systems of coordinates. And the load on the sphere is also constant. And here I have a schematic picture of the contact area. On the next slides, there are conditions for subregions in the contact area. We know that in rolling contact, the contact area divides into stick and slip subregions. And we don't know at the beginning the boundaries of these subregions. In stick subregion, there is this relation for shear and normal stresses, where mu is friction coefficient. And also in this subregion, the slip between points in contact of the sphere and the half space is equal to 0. In slip subregion, the shear stress and normal stress described with Coulomb law, and the next slide, I have a scheme of the kinematics of this problem, where the sphere is rolling over the half space, and there is a picture of the contact area. And we consider not only the longitudinal creepage, but also the spin creepage and the lateral creepage. And the longitudinal and lateral creepage is the main interest of in wheel ray and tire rod contact, but the spin is dominant type in angular contact ball bearing. These different creepages gives us the combination for, okay, here is the relation how we can calculate the slip vector for a rolling sphere. Here there also we take into account the shade displacement of the elastic sphere and half space, and X and RY is curvature radius of the sphere of the rolling body at point O. Okay, for normal stress distribution, we use Hertz solution, and we can consider elliptic contact area. And for calculation of the shear stresses, we use a variational method, which was described in the paper of Goldstein, Lazowski, Spector, and Fedorenko. And here, to find shear stresses, we need to minimize the functional in the contact area. And the slip vector is described by the summation, the creepage, the part which includes creepages, and the part which includes elastic displacements of the sphere and half space. In this problem, we also consider these dimensional parameters. Here I want to pay your attention to the dimensional parameters at the bottom of the picture. Here is longitudinal creepage, lateral creepage, spin, the parameter W, which describes the spin creepage, and also there is parameter gamma, which describes the coefficient of friction. Okay, let's see the results. The shear stresses calculated with the variational method have the following distributions. In this calculation, I have different longitudinal creepages, and the lateral and spin creepage are equal to 0. And here I want to say that parameter gamma is inversely proportional to longitudinal creepage. We can see that with the growth of this creepage, the maximum value of shear stress is also growing. And with the yellow color, here is presented the stick subregion. And with the growth of parameter longitudinal creepage, or with the decreasing of parameter gamma, we can see that the stick subregion is decreasing. And on the next slide, we can see that when we varying the parameter W, which described the spin creepage, the stick subregion, which before was symmetrical, now become non-symmetrical, and also the stick subregion area is decreasing. Okay, let's turn into another stage. It's stress state calculation of half space. For this, we need to calculate stress tensor components, and then we solve the characteristic equation and determine the principal stresses. And here we can see the relation for calculation of maximum value of shear stresses. Here I add an equation for one of a component of stress tensor, just to show that for this calculation we used the Boussinesq solution for concentrated normal force and Cerruti solution for concentrated tensile force. All these formulas you can find in the book of Johnson, Contact Mechanics. And on this slide, I would like to show the results of the internal stresses calculation, and compressive tensile stresses distribution. We can see that with the decreasing the parameter gamma, the compressive area is on the back side of the contact area, and the maximum value of tensile stresses is increasing, which corresponds the increase of the longitudinal creepage. And here there are some three-dimensional plots, contour plots of these compressive tensile stresses. Also, in the bottom picture, we can see that it was symmetrical. And okay, after the calculation of internal stress state, we can calculate the damage accumulated in the half space. Here we use the linear damage summation model, and for describing the damage function Q, we use the amplitude values of principal shear stresses and the parameter M, which characterize the damage accumulation model. Here, small q is the damage accumulation rate, and it depends on the values of amplitude values of principal shear stresses in the each points of half space. Also, in this calculation, we need to count we need to count the initial damage distribution in the material, which here is equal to Q0. And the failure condition in normalized version is looks like Q in the Q function is equal to so when we solve this equation, we will receive the number of cycles when the instance failure will occur. On this slide, I present the resulting distribution of principal shear stresses. We can see that with the growth of the spin creepage, the maximum value of principal shear stresses is increasing, but this parameter affects only the principal shear stresses in this close to the surface of the half space. It's when the z coordinate is equal to 0. And also the same situation when we change the longitudinal creepage and the principal shear stresses values changing only in the small subsurface area. And with these values of principal shear stresses, we calculate damage accumulation process for different parameters M. For small parameter M, we can see that after the first failure instant, the half space is starting to dominate. So this it's surface damage occurs, and when we take the larger value of M, we can see that there is non-zero thickness of the layer, which removes from the half space. And for the value for the parameter gamma equal to 1, the damage accumulation process is turns to surface damage. And also there is a damage accumulation process for parameter M 5.5, and here for all parameters gamma there are stages in the removal of surface material. Also calculate the same bursts for different spin creepages, and we can see that number of cycles which corresponds so with the growth of parameter M, the number of cycles is also increasing, and we can observe that at the value of parameter equal to 2.1, there is a constant rate of surface wear. So in this research, we calculate the contact and internal stress distributions for elastic bodies in rolling contact. And with these internal stress distributions, we calculate the damage accumulation rate caused by contact fatigue. And here, for damage accumulation, for damage function, we use amplitude values of principal shear stresses. The numerical study of the wear process shows that there is incubation stage, and after this incubation stage, there is a detachment of the layers of different thickness. Also, we show the influence of cleavage and parameters of damage function on the fatigue wear process. Thank you for your attention.
Thank you for your presentation.